Hello everyone, thank you for tuning in. I'd like to remind everyone the best way to learn from these problems is to try them honestly yourself and then look at these answers. Anyway, let's get into it. So, 3 different mass projectiles are launched from the top of a building, each with different angles of elevation. Each particle has the same initial kinetic energy. Which particle has the greatest speed just as it impacts the ground? Now, in this case, this kind of goes back to a problem we just finished on the other page. So, we had 3 projectiles all being launched from the same height but at different angles, and all of them had different masses. And so it's really a question of which one has the larger mass, because all of these energy equations, 1/2 mv squared, and mgh, all of them rely on mass. Now, it says they all 3 started with the same kinetic energy, which means that we can kind of forget about this part. When it comes down to the very bottom for each of these, all of their potential energy, which was the starting at the same height, is going to be converted to kinetic energy. So all had the same height, but not all had the same mass. So whichever one had the largest mass had the most potential energy. And that means they had the most amount of potential energy converted to kinetic energy. And the more kinetic energy you have, the faster you're going to be going. So again, very similar to the problem we had before, the one with the largest mass is going to have the largest speed at the bottom. So the one with the highest mass, the option was B for 14 through 18. Okay. So a worker pushes a sled with a force of 40 newtons over a level distance of 6 meters. If a frictional force of 24 newtons acts on the wheelbarrow in the direction opposite to that of the worker, then what is the net work done on the wheelbarrow? Okay, so we got 40 newtons and for 6 meters, and there's a frictional force of 24. So if they're talking about net work done, we got to figure out what net work is. Well, net work is just the work of all the forces added up. So we need to find the work for the applied force, that 40 Newton force, which I'll leave there, plus work for friction. Okay, so if we looked at this box, it's going to be traveling this way, or the wheelbarrow, always draw a box. The force applied goes this way, and the force of friction goes this way. So force applied will be a positive work, and force of friction will be a negative work, because all forces that go in the opposite direction of the actual object is negative. So let's do this. So work is force times distance, so Fa times the distance, minus force of friction times the distance. And so that basically turns into 40 newtons minus 24 newtons multiplied by the 6 meters. All right, so that's going to be 16 times 6, which I can't do in my head. 16 times 6 gives me 96 joules of net work. 96 joules gives me option D. Now, the work done by static friction can be positive, negative, 0, or any of the above. Now, we got to remember what static friction is. Static friction is when there's no sliding. Friction is just preventing any sort of sliding. So initially, you might think, well, that can't do any work because there can't be any distance because there's no sliding. But that's not necessarily true. An example I mentioned very often in class was a tire. A tire rolling on the road doesn't do any sliding, which means that it uses static friction. But static friction in this case does actual positive work, pushing the tire forward. So here's an example where it can do positive work. It can also do 0 work. And can it do negative work? Well, I don't think that even matters, because if positive is correct, which we know it is, and 0 is correct, which we know it is, it can't be A and C at the same time. So that means the answer, the true answer, has to be D. All of them have to be true. Because of weird examples like the tire rolling, the friction actually causes a force forward, and that's how cars work in the first place. So if static friction couldn't do positive work, then your car wouldn't move forward. Next question. A 1,200 kilogram automobile moving at 25 meters per second has its brakes applied with a deceleration of 8 meters per second squared. How far does the car travel before it stops? Okay, how far does the car travel before it stops? Well, let's see. We've got 25 meters per second, and then that's our initial velocity. Brakes are applied, and a final velocity is equal to 0 meters per second. Okay. Deceleration, negative 8 meters per second squared. All right. How far does the car travel before it stops? So you can apply the distance formula here. You could also do this with energy. I'm going to do this with the energy example. I think that'll be more useful. So how much kinetic energy does this thing start with? Well, that's 1/2 mv squared. So 1/2 times the mass, 1,200 kilograms, times that initial velocity of 25 meters per second squared. So that gives me the total kinetic energy, 0.5 times 1,200 times 25 squared. That gives me a lot of kinetic energy, 375,000 joules of kinetic energy. Now, some of you may be thinking, how do I get my answer for distance by just calculating the energy? And the answer is work. So work is change in energy, and it's also equal to force times distance. And so I know that in order to stop, it has to lose all of this energy. So that means I'm going to set my work, go to a blank page for extra room. So I'm going to set my work equal to negative 375,000 joules, because that's how much we have to lose. And I'm going to set that equal to force times distance. How far does the car travel before it stops? That means I would need to find the force. And so to find the force, I'm just going to use F equals ma, because they gave us the acceleration and we know the mass. So 1,200 kilograms times my acceleration of negative 8 meters per second squared. And so I get a force equal to negative 9,600 newtons. And so now I can take negative 375,000 joules, and I can divide it by negative 9,600 newtons for the force. That should be equal to the distance that I traveled. So negative 375,000 divided by that answer should give me a distance of 39 meters. If you found this another way, that's great, but I wanted to show you how you can use energy and work to get this answer. So in this case, the answer is A. Now, lastly, simple pendulum. 1 meter in length is released from rest when the support string is at an angle of 35 degrees from the vertical. What is the speed of the suspended mass at the bottom of the swing? Okay, that's a really great question. So we have a pendulum like this, okay, and it's going to swing down. It starts with a lot of potential energy because it's at this height, okay? So it's at this height above the lowest point. So if we wanted to find the potential energy, it would be mgh, with this being the h. Now, once it swings down here to the lowest part, it's lost all that potential energy, and that turns it to kinetic energy, 1/2 mv squared. So all of this potential will be equal to 1/2 mv squared, and so we can use this and solve for speed. So both sides have the mass of the pendulum, so we can get rid of that, and then we can solve for speed, and so we get 2gh over the square root is equal to v. So that means all we need to know is g and the height that the pendulum was released from in order to get the speed. Now we know g, it's 9.8. What is the to do this, we have to look at this triangle. Okay? So we know that length L is equal to 1 meter, but we don't know this height. But we know that this distance to the bottom of the height is also 1 meter. Okay? So it says that it's initially released with a 35-degree angle between the pendulum and the vertical. And we can use this to get our answer. So, if we did cosine of 35 degrees, that would be equal to this section here from the very top until the initial height. It would be equal to that section here divided by the 1 meter hypotenuse of this triangle. Okay, so this section would be 1 meter for the length minus the initial height, h. So now I've got this equation set up here to solve for the height. So multiply both sides by 1. Notice that doesn't change anything. That's equal to 1 minus h. Okay, so what's cosine of 35? Cosine of 35 is 0.81915. I like to not round when I'm dealing with these functions. Okay, and so now it becomes an algebra problem solving for h. Well, I'm going to add h to both sides and then subtract over this number. So that means 1 minus 0.81915 is going to be equal to my initial height, which is 1 minus this number. And so my initial height is 0.18 meters or 18 centimeters. So plugging it back in up here, square root of 2, 9.8 times 0.18. And then plugging that in my calculator. So square root of 2 times 9.8 times 0.18 gives me 1.88 meters per second, which is pretty fast. Looking at my answers, that would be option D.